Hey class, good afternoon. It's Friday, October 16th, and I'm going to record the lecture for today, which is on the variance, so variation and direct variation. So last time we were working in, I'm going to switch to share my screen. Last class, we were talking about variation in the supplement. That's section 12. And those are the problems that I'm going to do for you this morning. That'll help you with your homework. Your homework is module 9 from my math lab. And that homework's due Sunday night. And then some of you did not register my math lab in time or renew it, pay for it. You did the 14 days free, and now you can't get access to my math lab. Just do the alternate problems I put in that message from last time. And I'll try to dig that back out, which problem numbers they were. But I think if we go home and go to the last announcement, which would have been for Wednesday's class, right? Where we talk about direct variation. And last time we showed problems with direct variation. So we talked about your pay, your take-home pay varies directly with your hours or as hours worked. Your pay varies directly as your hours worked. The more hours you work, the more pay you get. The less hours you work, the less pay you take. But there's what's called a direct variation. And that variation is your rate of pay. So your hours times your rate gives you your paycheck. And that's called direct variation. And then we started in the supplement. Actually, these are the problems from the textbook. So this particular problem comes from the example from the alternate textbook, page 212. And then there's the second one with the water, or with the snow. So the water varies, the centimeters of water vary directly with the amount of snow that melts. So in that case, they gave us the water varies directly with the snow melting. W equals KS. That's direct variation, varies directly. It even tells you that in the problem statement. And so if we increase the amount of snow, then we're going to increase the amount of water. So first thing we do is we set up the equation. That's why I get this out here to the right here, set up the equation. All right, first thing we're going to do here is set up the equation. The water varies directly with the snow. And so we get the water, which we call W, and with the snow melting, we call the S. And you always have to put in that variation constant. So on all of these problems, you're always going to have a K. You know, what equals K times what's varying. And sometimes if it's indirect, then you have the 1 over X. If it's direct, it's K times X. It will show indirect here momentarily. So this was direct variation. So water varies directly with snow melt. We always put in this variation constant, which we saw is actually the slope of the line. So, and then, anyway, so water, they gave us the data in the book was they had 16.8 centimeters of water generated from 150 centimeters of snow. So then you determine what K is. So you isolate K, they give you 2 of the unknowns of the 3, isolate K and solve for it. So 16.8 divided by 150 gives me this 0.112. And then, so we went from 1 to 2, we solved for K, and then really 3, we set up this next equation. So now we're plugging in K. W equals 0.112 times S. And again, this is like that slope intercept, mx plus b, but these always run through 0, 0. Then they give us a second condition. Hey, what if under similar conditions, we had 200 centimeters of snow? Okay, so we go back to our equation. W equals KS. We've already solved for K, which was 0.112. And this time we know 200 centimeters of snow. So we just multiply 0.112 times 200 and get the amount of snow, oh, I'm sorry, the amount of water is 22.4 centimeters. Okay, clear. And then we did that last time. And again, that was in the announcements for 1014, which was Wednesday's class. We went over those 3 problems. And then I was just mentioning that if you did not happen to have My Math Lab, here's where these problems are. So if you don't have My Math Lab, go into section 2.5 of the alternate textbook and do problems 1 through 15 odd, 23 through 35 odd, and number 40. And the alternate textbook, if you go home and then click the additional textbook, and sometimes I called it alternate, and sometimes I called, oh, I called it alternate here, and I called it additional textbook here. Okay, and then today we're lecturing a little bit out of, or those examples that I gave you last time were from page 211 in the alternate textbook. Okay, so now today is October 16th, and we're going to do a few more problems. The problems I'm going to cover today are going to be, well, we can go back to that alternate textbook for a little bit, right? We start with direct variation, and we see these terms, when we know it's a direct variation problem when it'll tell us y is directly proportional to x. Or most of the time we see something like y varies directly as x. And at first I really didn't like that varies directly as x. As x what? But what it's saying is as x increases, then y is, it varies directly. So if x increases, y increases, which is what we're shown here in this graph. As x gets bigger, right, and this is the relationship because it's a slope, then my y is also getting bigger, right? So if I go further out, and then I'm gonna have to go up to my line. But the nice thing about linear variation is, as long as you know what the x is, and you know what the variation constant was, k, you can get y equals k, again, you know k because it's the slope of the line, times x. Or another way of writing it is right here. We say this is actually, there's some function of x where the value varies directly as x increases, right? That's my y value, but we say f of x. So then we plug in some x into the function. We know k and we compute y. Okay, so we said, like, in this case, let's say this is f of x equal to 35, right? So that's evaluating that function for x equal to 35, so k times 35. All right, so that's direct variation. Always sets up an equation that looks like kx, y equals kx. All right, we did these two equations last time. Again, what does it say? The water, the centimeters of water varies directly as s. So this is direct variation. Okay, alternatively, we have indirect variation or inverse variation. Inverse, so that means here we have the speed in miles per hour versus time. So suppose a bus is traveling at 20 miles an hour. I'm sorry, is traveling a distance of 20 miles. At a speed of 5 miles per hour, it will take 4 hours. So let's look at that plot a moment. So we got to go 20 miles. So at 5 miles an hour, it will take, right? So here's our plot, here's 5, and there's 5, 4. Okay. This is inverse variation. Now, if we go 10 miles per hour, we're still going 20, so it's going to take us 2 hours. And here's that point 10 comma 2. So as my miles per hour gets bigger, then my time is decreasing. So this is an inverse variation. The time varies inversely with speed. What kind of time? The travel time that's going to take for the bus to get there. So the travel time, K over R. I'm sorry, K is the variation, the coefficient is called the variation constant, and R is my rate. How fast was my truck traveling at, or what have you. So 20 is my rate constant. That's what's fixed. So typically we would start out with the time traveled equals K over the R, over the speed. How fast is the, right? So this shows us the situation where we have inverse variation. And here we would say that Y varies inversely as X, or in this case, the time taken for the bus varies inversely as the speed. So inversely means 1 over, just like when we did the perpendicular slope was in the case of the perpendicular slope, it was the negative inverse, but 1 over is the inverse. Right, the negative slope, the perpendicular slope was 1 over m, the negative 1 over m. Okay, so this is just inverse variation. So let's look at this first example. Clear all my drawings. So we have find the variation constant and an equation of variation in which y varies inversely as x, and then solve for it. So we have y varies inversely as x. So here this sets up y equals 1 over x times k. Or this is y equals k over x. But this is your inverse relationship, 1 over. So as I increase this, this number gets smaller. And if I decrease x, this fraction gets bigger, and therefore so does y. Right? If this gets bigger, my fraction gets smaller, which is what y is, time. So as x gets bigger, y gets smaller. So it varies inversely as x. So it goes the opposite of the way direction x is. And usually you see this as a type of hyperbola, where this is the inverse relationship as y varies inversely with x. So as x is getting bigger, y gets smaller down this graph. As x, right, if I go this way on my graph, it doesn't look like I'm changing my x, but x is getting a little bit bigger each time, and my y value is descending each time. As x gets bigger, my y is getting smaller. That's an inverse relationship. Okay, then the other part of the question said, they give us, okay, y is 16, so y equals 16 when x equals 0.3. Okay, so first set up the equation. Second, solve for k. So 16 equals 1 over 0.3 times k. Okay, we got this 0.03 in the denominator, if we multiply both sides by 0.03, then we're going to get 16 times 0.3 equals K. So that is, I don't have my calculator available. So we have 16 times 0.3 is 4.8. So 4.8 equals K. And then if you want to rewrite your equation, y equals 4.8 over x would be my final equation. Right, so K equals 4.8, and then they have 4.8 over x. All right, and then, so here we got a swimming pool example. The time required, well, so let's just do that one too. So example 4, page 214. So we have the time required to fill a swimming pool varies inversely as the rate of flow R into the pool. So the time varies inversely as the rate of flow, so 1 over R times K. Okay, I'm just using R, or you could have said rate. Okay, so if I increase the rate, then I'm going to shrink my time, just like this bus speed. Or if I decrease the rate at which we put water into the pool, then it's going to take more time. That's an inverse relationship. And so we understand the relationship now, we get the idea of the physics behind the problem. Now we're going to plug in and solve for something. So now they give us, now we got to solve for K. Right, so we had the time varies inversely. Let me rewrite that. Time varies inversely with the rate, right? The rate at which we're filling the pool. So this is where this 1 over R comes in. Time varies with 1 over R times K. And then we're going to solve for K with the data they gave us. So a tank truck can fill a pool in 90 minutes. Okay, so time, so now they give us time equals 90 minutes when the rate equals 1,500 liters per minute. Time equals this when the rate equals 1,500 liters per minute. Notice that they have a lot of units with this stuff. Most of our X and Y has not had units, and now we're dealing with units. And units are important because then you can see, helps you with the conversion factors or the multiple, what units are on your final answer, and see how the units cancel out. So we have time is 90 equals 1 over 1,500 liters per minute times K. So that's a rate. Now we just flip that over. So multiply both sides by the inverse. That's 1,500 times 90 equals 15. Multiply both sides by that. That's going to cancel out, equals K. So we got 1,500 times 90 equals K. I got to go back to 1,500 times 90. And so my rate constant equals 135,000. Okay. And then how long would it take to fill a pool at 1,800 liters per minute? Okay, once we solve for K, now we know T, we're going to plug that in. We have 135,000 over R. So first thing we do is set up the equation. They told us it varies indirectly with time. So time equals 1 over R times K. 2, we're going to solve for K. right? Then we're going to set up equation with k. So basically we're going to substitute k back in. And then we're going to solve additional problems. Because what we're going to do is we're going to solve the additional problems for that k in that relationship. So the next thing they asked us was, well, now that we've understand the equation, what happens if we make the rate 1,800 liters per minute? So the time equals 135,000 divided by 1,800 liters per minute. 135,000 divided by this is going to give me a certain amount of time. So 135,000 divided by 1,800 liters per minute, I'm going to get 75 minutes. Right, so as I increased my time, as I increased my rate from 1,500 liters per minute to 1,800 liters per minute, I decreased my time from 90 minutes down to 75 minutes. That shows this inverse variation. And the answer should be 75 minutes. Perfect. Oh, and they give you a little summary. Okay, and this is the same thing I've been saying, right? Determine whether the variation is inverse or direct. So you only have two options. It's not too bad. It's either k times x or 1 over x times k. Then you're going to write an equation in the form y equals kx or y equals k over x for inverse variation. Substitute the known values and solve for k, and then write the equation of variation and use it to find the unknown values in the problem. So they do want you to plug in that variation constant once you know what k is and get yourself down into, right, they're going to call this the variation equation, right? Even you've solved for the variation constant based off of some initial conditions, and then you're going to plug back in other conditions. The k does not change though. Once you've established what k is, you've set up the rate for this problem, for this scenario, this data set. And then once you've got that k, then you can solve for other speeds. You know, if we increase the rate to 2,000 liters per minute, how much time are we going to save? What if we get 2 trucks out there and increase double, you know, we can decrease our time. All right, and then the last part of it is combined variation. So y varies directly as the nth power of x. So now we're going to raise x to a power. So whatever they say, might say x squared or x cubed, or it varies inversely with the power of x. So then you just, and then jointly means 2 things. So y varies jointly as x and z. So that one is a direct variation. Anytime there's inverse, when you got to put it in the denominator, it'll say inverse variation. If not, it's direct variation. This y varies jointly as x and z. That means as the multiple x times z increases, then y increases. So that's the same. And we'll solve some problems. There's a few more examples here that you can look at in the textbook here, right? Find an equation of variation in which y varies directly as the square of x. So square means it's to the second power. So y varies directly. So k times x, but it's not just x, it's x squared. And now you just plug in what they gave you. So once you have your equation set up, that's the hard part. Make sure you remember to put in your k and then solve for it. You know, then solve for k. And then reestablish your, so in this case, k was 3, so y equals 3 times x squared. Find a equation of variation which y varies jointly as x and z. So here we got y equals k times x times z. Then they give us values. So now there's we don't know Y, we don't know K, we don't know X, and we don't know Z. We got 4 unknowns in this one equation here. But they give us 1, 2, 3 of them. So now we only have 1 unknown in our equation, and therefore we can solve it. So then again, we always solve for K first, plug in those initial conditions, solve for K, and then set up the variation equation. And then you would plug in more values. Once you solve for K, though, it does not change. It does not change from trial to trial. Find the equation of variable in which Y varies jointly as X and Z and inversely as the square of W. So Y varies, so that takes a minute to read. So Y varies, Y equals K varies jointly as X and Z, so that's K times Z, so K times X times Z, and inversely as the square of W. So that means W is on the bottom, that's in the inverse, and it's actually the square of W, which means W times W, or W squared. And there's our exact K X times Z over W squared. Same idea, plug back in. They give you Y, X, Z, and W. 3 times 20 is 60. 60 divided by 4 is 15. Divide the 15 to both sides, and K equals 7. All right, so now we got put that 7 in for K, which is what we're done down here. And they showed it in either way, the constant times the values, or put it on top of in the numerator. Okay. Volume of a tree. This is pretty cool. The volume of wood V in a tree varies jointly as the height and the square of the girth. Girth is the distance around, like the circumference. Okay, so let's draw that out here. The volume of wood varies, so V equals K times, now it says it jointly as H, so K times H. And jointly means there's 2 of them, and the square of the girth, so K times H times G squared. The volume V in a tree varies jointly as H and G squared. And then solve for, then they're going to give you the values. The hard part's making this first equation. Once you have your equation, again, plug in all the unknowns, solve for K, and then rewrite your equation. And then it says, once you've solved for K, like we did here, we got 3.2. Now, what is the height of a tree whose volume is 960 meters and whose girth is 2 meters squared? Okay, so what is the height of a tree? So there's H, we don't know H. We know K, so whose volume, so they already gave us the volume. So they gave us, in our equation over here, we're gonna know V, we know the girth, and we know K, and we're gonna solve for H. So plug in for the V. We already got K. We don't know H, and they give us the girth. Multiply 3.2 times 4, get those to the other side, and solve for H. So that tree is 75 meters high. That produces that volume. And then on to the homework. All right, so let's do a few out of the syllabus, or not of the syllabus, out of the supplement. So let's peek at the supplement. And we're going to do section 12 in the supplement, just to make sure you know how to do these problems. So y varies directly as x, and y equals 12 when x equals 8. So supplement section 12. Okay, y varies as x, so that means y equals k times x. Y varies directly as x, and then they give us two conditions. Y equals 12 when x equals 8. So y equals 12 when x equals 8. So we have 12 equals k times 8, and 12 divided by 8 equals k. And I think that's what, 1.5. So k equals 1.5. And then just plug it back in now, so we have this equation, y equals 1.5 times x, right? And that's basically the slope of a line, up 1.5 over runs. Note, in this case, b is equal to 0, the y-intercept. So we've got some equation here where the slope is 1.5. And if we remember, right, that the tangent of theta equals m, they give us the slope here, which is the 1.5. We don't know what theta is, so theta equals the tangent inverse of the slope, which was 1.5. So theta equals, calculator, got my iPhone here. Got to turn it sideways to make it turn on the more advanced operations. So my slope was 1.5. And if I take the inverse tangent of the slope, I get the angle. So that's a 56.31 degree angle, which has a slope of 1.5, right? Y equal mx plus b. In these direct variation problems, they go through 0, 0, which means your y-intercept is 0. So that means, right, that doesn't exist, right? It's like saying plus 0. But in our equation, y equal mx plus b, this looks very similar, right? We've got y equals 1.5 times x. That variation constant is the slope. And then this, there is no plus b because they run through 0, 0. So if I have no, right, that varies directly as x. So if x is 0, then y is 0. If I increase x, then I increase my y value. Okay, so that's number 1A. 1B, y varies inversely as x. Y varies inversely as x. So that means y equals 1 over x times k. Inversely. Y equals 5 when x equals 4. Y equals 5 when x equals 4. So plug that in. So we have y equals 5 when x is 4. The only thing we don't know left is k. Multiply both sides by 4 to get rid of this. So 4 times 5 is 20. That's equal to my k. And then I can plug that in. What's my final equation? It's 1 over k. I'm sorry, 1 over x. 1 over x times 20. Or y equals 20 over x. Right? If x is small, like 2, y is 10. Right? So now you could like plot it a little bit. If x is 2, then y is 10. So it's way up here. Right? If x is 4, 20 divided by 4 is 5. Right? If x is 6, 20 divided by 6 is about 3 point something, right? It's coming down even further. When X is 10, when X is 10, Y is 2, right? So we get this, what's called inverse relationship. As X gets bigger, my Y values are coming down. That's an inverse relationship. And in the opposite way is true too. As X gets smaller, as we're going this way, then my Y values are getting bigger. All right, that was number 1B in the supplement. All right, let's look at 1C. Y varies jointly as X, right? So that's Y equals K times X and the square of Z, so that's times Z squared, so X times Z squared, and inversely as W. So that's Y equals K time, right? Because it varied jointly with X and Z squared, and the square of Z is Z squared. So Y varies jointly as X and the square of Z, and inversely with W. So that means that as Y varies directly with these guys and inversely with W, which is kind of like the ideal gas law, right? You got something like PV equals nRT, but you could say the pressure equals nRT over the volume. So the pressure varies directly with the number of molecules, this is that rate constant, and the temperature, and inversely with the volume. All right, then I'm gonna let you guys plug these in here for X equal 2, plug in X equal 2, Z equal to 5, and W equal to 15. Solve for K, and then set up the final equation, right? Set up the final equation with Y equals, right? So I'm gonna let you just plug in these values, solve for K. You know you got all the pieces, solve for K, and then finalize the equation and check your answer in the back. All right, so on to problem 2. Oh, here comes the ideal gas law. So number 2, find the variation constant and variation equation, same thing. The volume of a given mass varies directly as temperature. So the volume of a given mass varies directly as temperature. So you got K times T, and inversely as pressure. And then they give you the equations, right? So volume varies directly with temperature. So you got to bring in your K first, K times T, and inversely with pressure. And then you plug in your values and solve for K. So they give you, in your initial condition, your volume is equal to 150. Your temperature is equal to 25. And your pressure equals 10. Right, so this is the initial condition. This is the initial one. So plug in, solve for K. So V is what, 150. We don't know K. The temperature is 25, and the pressure, and the pressure is 10. So multiply both sides by 10. We got 1,500 over here. 1,500 divided by 25 equals K. 1500 divided by 25 is K, so K equals 60. Okay, so now you know K, and now we go back to our original equation, right? We go back to our original equation, plug that in. So now V equals 60 times the temperature divided by the pressure. Then the second half of the question was, now they give us, so once we know K and we solve for it, now they give us more data. So now, right, so now we're going to solve the next part. Solve the next part. K already found, so use it. Right, solve for the next part. K has already been found, so use it. And what was the next part again? The next part is temperature equals 45, and the pressure equals 20, and they want to know what is the volume. Right, so the second part, they tell you the temperature is 45, the pressure is 20, they don't know the volume. Okay, so volume is what we're looking for, but luckily it's already set up nicely. So that's 60 times the temperature, which is 45, divided by the pressure, which is 20. So V equals 60 times 45 divided by 20. So that's 60 times 45. I'm going to divide that by 20. So V equals 135. And whatever the units were, the units are in centimeters cubed, as they show here. You should always check to make sure all your units match, because sometimes you have to do a conversion between like grams and kilograms. But in this case, it's going to be centimeters cubed. All right, then we're just down to the last part. Clear mouse. Okay, so translation. The amount of fuel consumed by an aircraft varies directly as the length of time increases. So we have fuel, F, varies directly, so that's K times the length of time, T, increases, and inversely as the gross weight decreases. So, and inversely. Write the equation that represents that variation. Right, I think you can do that pretty easily. If the answer's in the back of the textbook, I'm sure you can figure that out pretty quickly. The amount of fuel of an aircraft varies directly as the length of time T increases. So you got F equals K times T, and inversely as the gross weight. So inversely over W. And they really shouldn't really say decreases there, because that kind of implies something else, but that it's just KT over W, right? So you should have something like F equals KT times W. Write the equation, write the translation for this. So this time you got the W squared on the bottom, so that's that inversely with W squared. So Y varies jointly with K and X, and inversely with the square of W. And again, you can check that one in the back. Okay, I will be online today during class. Email me if you got questions and troubles, but if not, I'm going to let you guys work. These notes are going to be in the announcements here shortly, and we will see you on Monday. I will have your grades updated this afternoon. I do have to be in and out, so I won't be available all during class period, but I will be there for the start of each class period. And if you got questions, we'll take care of them. Okay, so working on homework, got a test next Friday. The test, work on practice test 1 and 2 in the back of the supplement. 4 problems. All right, we will see you next time, or see you this afternoon in class. And have a good afternoon. Be safe. Watch out for motorcycles.